right, thank you for being here. I'm Luca Antiga, and this is Thomas Viehmann. We both work at Lightning AI, and today we're going to talk about Thunder. It's something that we presented a while ago, I guess, like a year and a half or something. And we're going to update you on the developments, or for those of you who don't know what it is, we'll tell you why we're doing it and what are the principles. And so we're Lightning. We developed the Lightning AI platform. I don't know how many of you know it. Just go on there, lightning.ai. You get a free account. You get free credits to use GPUs. And it's really a cloud platform that is overfit on PyTorch. You can do whatever on it, but PyTorch works really well on there. We just launched a few initiatives with the Meta organization. You can take a look at the new stuff like Monarch, Forge, and OpenEnv. Just a call out for you guys. And then we also deploy models for inference. So it's a platform where you can go from training to inference, and you can optimize. You get optimized inference out of that. We are on artificial analysis recently, thanks to the work of Liana here in the crowd. So that's good. And part of what we do is not just provide compute and a platform, development platform for our customers, but also we help them making the most out of the compute by optimizing their models on our compute, using a stack of open source tools that we have. One of them is Thunder. And today I'm going to talk about how this works and how we can optimize things for our customers. And our sweet spot is not just to call a compile method and out of the box you get a speed up. We have a budget of a few days, few hours, few days to optimize a model. So we want to spend the time, for example, to make sure we have a full graph, a full trace, and everything can be interpreted by our compiler. And we can run it, inspect, transform it. So the ability for us to extend the compiler and to make it capable of understanding the model a bit better and writing custom transforms so that we can take the computation to where we want it to be. That is our job. And so this is the design space that we are operating in. It's really like a tool rather than a out-of-the-box compiler. And this is what I mean. So suppose you have source code, a little more complicated than a sequential with a couple of linears, but that's the principle there. And you want to execute it. And now you're unsatisfied with your GPU utilization. What you can do is you can compile. So compile here is not torch compile. It's just for some definition of compile, right? And you have some knobs, which are usually compiler flags. And then you get some performance out, and you look at the utilization, maybe good, maybe not good. So you have some knobs you can turn there. And the other opportunity you have is you go back, and in the source code, you can tweak. You can put context managers. You can express your computation a bit differently. And then you see the effect that it has on the utilization that you get on the other side when you throw it to the compiler, and you iterate in that space, and you keep touching your model. And you can do it model by model, but it's really hard to port whatever you did from one model to the next. So if you're exploring different variations of your thing, then you get kind of a combinatorial explosion of the work you're doing to optimize a particular model and how you do port the same things to another model and so on. And so your model becomes like you need to dress it up a bit. And we believe that there's a kind of a better way to do it that gives you more control, which is, and we saw this for those of you who have been at the keynote for torch.compile. Torch.compile is now evolving into a toolkit. So we found a common sentiment there. So you have source code, you acquire it, you have an IR, and we want to make IR transforms, so the operations that compose your computation, and the way you transform them programmatically to make it as developer-friendly as possible. Because you shouldn't be a compiler engineer to be able to take a computation and transform it into something else that is more akin to the performance, the characteristics that you want, or you make a computation distributed. So you write your model in math in PyTorch. PyTorch models is a great way to write models. And how do you scale and optimize it? You can do it at the IR level if the IR is expressive enough for you. And I can show you an example. We show you an example in this talk. And then the transform that you apply to the IR can be made portable across models. So you can apply a certain distributed strategy that turns a single GPU model into something that runs across GPUs or across machines by placing collective calls at the right place. And you can do that in a generic way so that it is composable and you can write it once and apply to many models. Maybe not to all models, but maybe to the models around the model you're exploring there. And then you send it to execution. So, you know, our goal is kind of decouple the research that our customers do, and they come at us with a model, and maybe we can tweak it and make it a bit better. But then our work is the central box there. And so we would like to create a tool that allows us to do this work in the most frictionless way possible. And there are examples of that out there. If you look at DeepSpeed, there is something called DeepCompile. And I think they have a blog post in there that describes Thunder really well. Like existing approaches, DeepCompile automatically applies parameter sharding, communication scheduling, and memory-aware execution at the compiler IR level, enabling global analysis and optimization that are difficult to express in traditional frameworks. This is kind of the space where we're operating. And what is our hypothesis is that I don't know if Thunder will be the way, if torch.compile will be the way, if DeepCompile will be the way, but there is clearly a gap in the space of program transformations that will be filled by one or more tools that we will use to make our models distributed, scalable, and performant. Okay, and so whatever it is, we describe our experience and design ideas, and then I hope we can all come together and build something that has the power and expressivity of PyTorch that researchers like, because you shouldn't be a compiler engineer in order to do this kind of work. That's the gist of it. So if you go into DeepSpeed compile, you can see that they implemented a system of passes. Passes and transforms are kind of like doing as the same term. But this is not just for training. If you go into VLLM, for example, and you go in how VLLM handles compilation, they also have a system of passes. But there are many ways where you can make writing a transformation of IR aware, for example, of its surroundings. And what is the surrounding of a functional IR? Is the NN module. So in Thunder, we built a way to to have transforms applied at different life cycles of where a transform can be applied at the module level, at the there are many places when Thomas will show a few of them, but there are many moments, and if you are tidy there, you benefit from being able to compose different ones, different transforms. For example, I can make a model distributed by sharding the parameters. Now, if I shard those parameters, then my tensors will be smaller, right? So what I want to do is delay materialization of those tensors to after I apply the transformation, right? Because otherwise I would go out of memory on individual node. And so there's a certain sequence of things that will lead me to maybe load weights. And the weight loading needs to be aware of the fact that I applied a sharding transform before, because otherwise I'm loading the weights that are like too large for my model, right? So there's a certain sequence of things that need to happen. And in Thunder, we try to make that easy to manage and keep in your head and develop upon. So this is Thunder. Design principle, decouple model from optimizations. Easy IR, we have an IR, and we'll see it in a second, that is just Python, and it's easy to inspect, profile, and run. We have a rich, full graph transforms without graph breaks, And then we have a way to dispatch different sections, different portions of the IR to different executors. This is what the IR looks like. Actually, this is a it's the most high-level view of the IR. And here you have there's a bit more to it. This is the purely functional computation trace. And we have then a prologue and an epilogue that go from NN module land to purely functional back to NN module that you can also transform. And it has different functions. And then this is an operation, a linear. And we have HLO-like decompositions for those of you who know JAX. It's very similar to JAX internally, where you have primitives that we decompose into, and then each executor can choose whether to take and execute the high-level operation or take the decomposed operation. And usually, for example, decomposed operation, the primitives don't have automatic broadcasting, so you will see the broadcast operation, and then the operation on the broadcaster tensors and so on. So there's a bit more detail. And our trace is very expressive on that front. And interestingly, we wrote a C Python interpreter in Python to be able to trace through generic programs. And so we understand the bytecode, and we can then extend the interpreter. So it's really easy if I have a construct that the interpreter doesn't understand to bypass that hurdle towards getting a full graph by extending the interpreter in Python to be able to say, okay, yeah, I know you don't understand this, but trust me, do this thing when you encounter this function. And then we can more easily go from unoptimized to optimized by obtaining the full graph of the model. And this is an example of what we do when we apply a distributed transformation, in this case FSTP, to the IR, and we insert, you will see that in this case, the batch dimension changes in size, goes from 4 to 2, and then we have distributed primitives. And you can do it programmatically, right? And you can do many more of these things, like autodiff, or like autograd. Autodiff is a transform for us. So we obtain the backward trace. And so you can transform the backward trace just as easily as you transform the forward trace. And so you have full control of that. You can apply mixed precision, offloading. You can decide when to offload in the lifetime of the trace, and so on. And all these things are composable. This is the different executors that you can dispatch, and each executor can claim portions of the trace to execute. So it's very flexible and extensible there. And now I'm passing it to Thomas. He will demonstrate Llama 4 Scout on a single H200 and how to get it to work on there, and then in the some of the developer journey. So Thomas.
Yeah, hey, and the code that I'm going to show you, it will be a bit dense, but it's also available as a studio, so you can dive in yourself if you want to. And also, this is like my first PyTorch conference, so I may or may not know what I'm doing. Okay, so let's take a model, say Llama Scout from Transformers, and I want to run it on an H200, because that's one of my favorite GPUs at the moment for like coolness and availability. And so Llama Scout comes as a big float 16 model by default, and it has 109 billion parameters, which means it doesn't fit on the GPU as is. But we can take 2 layers and just run through it. It's on HuggingFace Transformers, so let's grab it from there and run it. And it's as easy as running Thunder.compile on it here. And we have a recipe that says, well, yeah, HuggingFace Transformers, because they have a few particularities that we want to cover. Okay, we do this. We get a timing that's roughly similar to what Transformers do anyways. So you might ask, like, what's the point? And whenever I think there might be perf left on the table, what do? Well, if you want to optimize, you have to measure first. If you don't measure, it's not optimization that you do. And so we do use the PyTorch profiler, which is really great in producing traces that you can consume. And we have a plugin to the compile call, which is a transform style thing that essentially lets us profile in some detail. And so this might be my favorite slide. What you see is that for each line of the code in the intermediate representation that Luca showed you, we have a block in the profiler. So we really see like what gets executed for what line of code. So here you have a NVFuser, which is from the NVFuser from our NVIDIA friends. And you see that also on the bottom line, you see the CUDA kernels. It traces the stream. The bottom line is the CUDA kernels. And we annotate with the exact line of source code in the intermediate representation that this comes from. And so it's a simple trick, but it's super helpful. And what we see is that we have like those gaps in the bottommost row. And that means that we have bad GPU utilization there. And so one of the things you can do is you can use CUDA graphs, which we again provide as a reduced overhead plugin. And this will know like what operations are CUDA graphable, what you need to do with the inputs, and work with the restrictions that you have. And you see that you can get a decent speed up by applying it because you essentially eliminate those gaps. Okay, so, but this is just the 2 layers. We want to run the full thing. Well, if big float 16 doesn't fit, maybe FP8 fits, and indeed it does. And what we do is we created a 8-bit transform that uses NVIDIA's TransformerEngine to execute the model in 8-bit. But we do this without compiling, without modifying the transformers, but by compiling it with this extra transform. And so what we get a model that actually produces text as it should be. And the other part that we do is that we add a materialization transform that also Luca mentioned. This allows us to instantiate the model on the meta device, so it doesn't take any memory. Then we transform it to 8-bit, which would fit then on the device, and then we actually put it on the device. And you can choose whether you want to initialize the weights from a state dict that has been transformed or from one that hasn't been transformed, because what the transforms do, and this is like one of the key things, that the transforms consistently transform the module itself, the parameters you have, the computation, the trace that you have, the program, and the state dict. So, and if you want to, you can also have a backward pass that if you want to save the state dict in the original form. And so the FP8 transform will quantize the weights. It will replace the linears with quantized linears and also the MOE. And then it will quantize the state dict when you load the state dict. And the materialization, it will not change the computation, but it will allocate the memory, initialize things through the state dict by using the transform mechanism that you see on the bottom row. And so the important part here is that because we have all these things bundled in the transform, we have like an invariance that the transform and the code and the model and the data when you load the weights match before and after the transform, which allows us to combine transforms arbitrarily. Okay, so when we do this, we get relatively decent GPU perf. I didn't put out another trace, but you can like have a sanity check by using the Lightning platform, which will give you a GPU utilization over time. And so the small spike here is the time where we run the model. Okay, So this is the transform. If you want to see it in more detail, you see that the transforms has a part that works on the module, which essentially picks out the linears and then adds the new, it quantizes the weight and adds the scale information. Then you have the state dict transform that does that on a concrete state dict that you get. There's really a PyTorch dictionary, just like an ordinary state dict. And then you have the transform of the computation, which essentially searches for linear layers and then, or for linear operations in the trace, and then replaces them with TransformerEngine powered linear operations. And that's all there is to it. But by using this as an interface, we have like relatively powerful transforms when we combine multiple of them. If you have more fancy hardware,
yeah, this is something that our friends at NVIDIA have run on Llama 4 Maverick, deployed on B200s. There's a lot of experimentation going on there with tensor parallelism. And in this case, we're actually consuming D-tensors. So normally our distributed transforms operate on something that has just regular tensors, but there's also work undergoing to support D-tensor style parallelism and being able to interpret what the tensors want to do to the data so that we can generate a trace that is consistent with that. And we have a speed up over eager, and there will be more work done around here, particularly related to the use of the lower precisions like NVFP4 and such, that can follow more or less the same approach as what Thomas showed. All right, so as I just mentioned, Thunder is developing collaboration with NVIDIA, and we would be very happy to have people join, and also tight collaboration with PyTorch, the main PyTorch project, because it's very PyTorchy, right? What we showed kind of embraces the NN module and doesn't play too many tricks. It's just like pure PyTorch and pure PyTorch code transformations. And even the IR is basically PyTorch. So we hope that some of our ideas will end up kind of blending in more and more with the ecosystem. And yeah, sometimes there's a repo. Sometimes we meet in our little rooms and we chat about Thunder. So there's a bunch of episodes, I think 20 something, 30, I don't know, where Thomas and I can scratch our heads on different problems, and you're happy to follow or join in at some point. And we call it like deep learning compilers and how this sausage is made. And it's not always pretty. Okay, yeah, thank you. I think you need to ask for questions. Yeah, any questions, of course? No questions, okay. Oh, there's one there. Yep. And also we'll be at the booth, so if we want to meet us afterwards, we'll be happy to. Yep.
Oh, hi, thanks for the presentation. I have a bit of a noob question, but so you mentioned that there's an interpreter that goes through the current model and does the various passes. So I'm curious, I don't think I saw it, but what are the tricks, for example, of doing that? Like, where are the low-hanging fruit? Is it the synchronization? Is it the compute comps overlap? Like, where, like, how far have you gotten into doing that compilation and interpretation process, and how much more do you think there is?
I mean, you get control, right? So I think, well, if you want to also address it, of course, but you get a lot of control, fine-grained control on the forward and the backward on where you want to position your communication relative to your computation. So ideally, you could also combinatorially explore where you want to position them in a very intentional manner if you have a very specific workload that you cannot easily do with other frameworks, right? Because you don't have every operation laid out in front of you. I don't know if you want to. Yeah. Okay. So I said it right. All right. No, but yeah, it's all about control essentially, and being able to manually and programmatically do things to your computations that you want, that you need, and not rely on kind of abstractions being in the way, as I should. Yeah. Yep. Another question there. There's a mic coming. Sorry.
And it's going to be the last question.
Yep, last question. Yeah.
So if there are multiple executors supporting a given operation graph, is there a way to auto-tune in Thunder?
Yeah, there is a prioritization that you can decide. And then it's based on a claim thing. So each executor will have a function that returns whether or not that executor wants to take up that operation or a sequence of operations. And so if no one picks it up, it will be the fusion operator, and if it fusion executor. And if the fusion executor doesn't pick it up, then we have a fallback into kind of PyTorch, for example, Eager. And you can decide which executor to put in the mix. You can customize the claim very easily by specifying a function. And then you can put them in a certain sequence where the topmost gets the priority of choosing. And if that one doesn't choose, then it goes to the second and so on. But we can make it even more elaborate. Like it's all Python, so it's not very complicated.